took less than 5 seconds. What began as a quiet morning observation ended in shock as the ocean surged forward with violent intent. From a third-floor balcony overlooking the beach, hotel manager Jay Williams watched as a massive wall of water rose without warning. The wave did not roll in gently. It slammed directly into the lobby of the boutique hotel below, shattering glass, flooding corridors, and erasing the invisible boundary between land and sea in a single moment. There was no siren, no countdown, no time to react. Across California's coastline, similar scenes were unfolding. The Pacific Ocean was no longer behaving like a predictable system governed by tides and seasons. It had turned aggressive, relentless, unfamiliar. In the early hours before dawn on Christmas morning, powerful waves battered the entire coast. These were not ordinary winter swells. They exceeded forecasts, overwhelmed coastal defenses, and struck with a force that scientists had not expected to see under current conditions. Emergency alerts flashed red across mobile phones. News broadcasts abandoned routine updates and shifted into crisis mode. Fear spread quickly. For millions along the West Coast, danger was no longer theoretical. It was visible, audible, and shaking the ground beneath their feet. California was no longer watching a storm pass offshore. It was trapped inside a rapidly escalating coastal emergency. And scientists were already saying this was not just another storm. This event marked something far more serious, not just weather, a breakdown in expectation. From Humboldt County in the north to Santa Monica in the south, researchers dropped their usual cautious language. Warnings became blunt, direct, urgent. The ocean was delivering energy levels capable of removing entire sections of coastline, not inches of sand. Entire neighborhoods faced the possibility of permanent land loss. What alarmed experts most was not just the height of the waves, but the combination of forces converging at the same moment. Elevated sea levels, intensified wave energy, structural weakening of cliffs and bluffs already compromised by years of erosion. The Pacific was no longer a background force, it was the primary threat, and communities felt it immediately. The night the coast began to move, residents along the shore were jolted awake by the sound of waves hammering cliffs and seawalls. Houses trembled, streets echoed with rushing water. In darkness, families grabbed essentials and fled toward higher ground, unsure whether this would pass or worsen. In some areas, roads that had been dry just hours earlier disappeared beneath floodwater. Sirens cut through salt-filled air. Emergency announcements blended into the roar of the surf, repeating a single command: move now. Every second counts. Cars crawled through flooded streets. Evacuation routes changed by the hour. For many, the sense of control vanished entirely. This was not a temporary inconvenience. It felt like something was breaking. Inside emergency operations centers, data streamed non-stop across glowing monitors. Floodplain maps were redrawn in real time. Evacuation zones expanded again and again. Families crowded into shelters as scientists confronted a question they had hoped to avoid. Were they witnessing the beginning of a permanent transformation of California's coastline? The invisible battle beneath the surface. What played out on beaches and boardwalks was only part of the story. Beneath the sand, underwater sensors recorded incoming wave energy far beyond normal thresholds. But they also detected something else, something quieter and more dangerous. The land itself was responding. Each wave delivered not just water, but pressure, stress, structural strain. Seawalls designed for once-in-a-century events began to crack and fail. Bluffs weakened under repeated impact. Ancient layers of sand, clay, and bedrock absorbed shock after shock. In some locations, erosion advanced slowly. In others, it struck suddenly and without warning. Entire sections of coast collapsed between one tide cycle and the next. This was no longer erosion as it had been modeled. It was destabilization. A compound disaster takes shape. Inside laboratories and research centers, the mood darkened. With every shattered window and collapsed deck, deeper fractures formed in California's coastal security. Long-held assumptions began to fall apart. The belief that beaches would recover, that cliffs would retreat gradually, that the coastline could absorb extreme events and bounce back. Experts were clear. This moment would leave scars that could not simply be repaired. According to seismologist Dr. Lucy Jones, the crisis was driven by an unprecedented convergence of hazards, a compound disaster. Multiple threats amplifying each other beyond anything historic models were built to handle. New terms dominated briefings: tsunami watch, compound hazard, seismic stress, massive surge. These were no longer abstract concepts. They became daily realities for millions. And the trigger may not have originated near California at all. The shock that crossed the Pacific. On January 10, 2026, a magnitude 6.7 earthquake struck near Humboldt County. Initial analysis suggested no tsunami threat, but that quake was only the opening signal. Days later, a far more powerful seismic event erupted off the coast of Russia. A massive magnitude 8.7 earthquake sent energy racing across the Pacific basin. Within minutes, global alerts were issued. California's entire coastline was placed under tsunami watch, a rare escalation. Deep-sea buoys registered abnormal wave behavior as the energy moved eastward. But scientists noticed something critical. The Pacific was already primed. Months, possibly years, of environmental stress had built silently beneath the surface. Slight increases in sea surface temperature, subtle shifts in ocean currents, loss of protective sandbars and kelp forests that once dampened wave energy. Individually, these changes seemed small. Together, they amplified destruction. By Christmas morning, forecasts that had predicted elevated surf were no longer valid. Advisories escalated rapidly. Counties across Southern California entered emergency status. Beaches emptied. Helicopters surveyed homes perched on eroding cliffs. Boardwalks vanished under single surges. As dawn broke, one truth became unavoidable. This was not just flooding. This was the coastline recalibrating itself, and some of the changes unfolding would not reverse. As waves continued to batter California's shoreline, scientists realized the most dangerous forces were not visible from the surface. What was unfolding beneath the sand, beneath the roads, beneath entire communities, was far more alarming than broken seawalls or flooded streets. The coastline was not just being eaten away from the outside, it was weakening from below. In research centers across the state, seismic monitors began recording subtle anomalies, not earthquakes in the traditional sense. No sharp spikes, no violent ruptures. Instead, the signals were slow, drawn out, and strangely rhythmic. Frequencies too low to feel, too structured to ignore. These were the kinds of signals that make scientists pause. The data suggested stress redistribution deep beneath the coastal shelf, pressurized fluids moving through fractured rock, slow slip behavior occurring without a clear fault rupture, processes capable of destabilizing land long before any collapse becomes visible at the surface. To the public, the coast still looked intact in many places. To researchers, it already was. When sensors tell a different story. Underwater instrumentation installed years earlier for tsunami detection and climate monitoring began delivering troubling patterns. Each surge from the Pacific delivered not just water, but energy force transferred directly into the seabed. Over time, that energy accumulated. In stable systems, the land absorbs and disperses it, but this system was no longer stable. Sensors embedded beneath beaches and bluffs recorded micro-deformation, small shifts in elevation, millimeters at first, then more, not enough to trigger alarms individually, but unmistakable when viewed over hours and days. This was not normal coastal erosion. It was structural fatigue, and the stress was spreading inland. Subsidence, the quiet collapse. One of the most concerning developments was land subsidence, the slow sinking of ground beneath coastal communities. Unlike dramatic cliff collapses, subsidence happens quietly. Roads dip, foundations crack, drainage systems fail. By the time it's visible, the damage is already advanced. Satellite-based INSAR imagery revealed that certain coastal zones were sinking faster than predicted. In some locations, ground elevation dropped measurably in less than 48 hours. Areas once considered safe under flood maps now sat lower than surrounding water during peak tide. This changed everything. Flood barriers designed to protect communities were suddenly the wrong height. Stormwater systems reversed flow. Saltwater crept into underground infrastructure, corroding pipes, electrical conduits, and communication lines. The coast wasn't just retreating, it was sinking. Infrastructure under pressure. California's coastal defenses were built for a different reality. Seawalls, levees, and breakwaters were engineered based on historical extremes, storms expected once every 100 years. But those assumptions no longer held. Waves arrived higher, faster, with more energy. Seawalls fractured under repeated impact. In some areas, water overtopped barriers that had never been breached before. Roads collapsed as erosion hollowed out the ground beneath asphalt, leaving only thin surfaces unsupported. Power substations flooded. Cell towers lost connection just as emergency alerts were most needed. Backup systems failed under saltwater exposure. Communication gaps spread faster than crews could respond. Emergency messaging shifted tone, from guidance to command. Leave now. For some residents, the warning arrived too late. A chain reaction of failure. As coastal defenses faltered, secondary disasters followed. Rivers backed up as high tides blocked drainage outlets. Stormwater had nowhere to go. Neighborhoods flooded from below, not from rain, but from the ocean pushing inland through underground pathways. Mudslides erupted in saturated hillsides. Cliffside roads sheared away without warning. Inland communities, far from the beach, suddenly found themselves dealing with flooding they were never prepared for. The crisis was no longer confined to the shoreline. It was spreading. Emergency planners watched decades of hazard models fail in real time. Evacuation maps proved outdated. Insurance assumptions collapsed. Entire neighborhoods once classified as low risk were reclassified overnight. And there was no easy fix. The science behind the fear. What made this event especially dangerous was the way multiple forces amplified each other. Rising sea levels reduced the margin for safety. Stronger waves increased erosion. Subsiding land lowered natural defenses even further. This is what scientists call a compound hazard. Each element alone is manageable. Together, they overwhelm systems. As one coastal geologist put it, you're not just losing land, you're losing the foundation that land rests on. This realization forced an uncomfortable conclusion. Some parts of California's coastline may no longer be defensible. When rebuilding isn't enough, cleanup crews worked non-stop, but progress was undone with each tide cycle. Sandbags washed away, temporary barriers failed, repairs became temporary by default. For families who had lived near the coast for generations, the emotional toll was heavy. Homes once considered permanent now felt provisional. Safe zones shrank, uncertainty grew, and scientists knew the worst might still be ahead. The systems driving this crisis did not stop when the waves briefly receded. Stress remained locked beneath the surface. Water tables stayed elevated. Fractured ground continued to weaken. The coastline was still moving, and the next trigger, another storm, another seismic event, another surge, could push already strained land past its breaking point. A new reality takes shape. By nightfall, one truth became undeniable. California's coastline had entered a new phase. Extreme events were no longer rare. The land was no longer static. The margin for error had vanished. What had once been considered safe was now uncertain. What had once been temporary damage was becoming permanent change. The coast was not just reacting to the ocean, it was surrendering ground. And in part 3, the focus shifts to what scientists uncovered next, evidence hidden inside collapsing cliffs, chemical signatures that shouldn't exist, and why researchers believe the danger may be coming from deeper than anyone expected. Once emergency crews stabilized the immediate danger zone, scientists were finally allowed to do what they do best: examine the evidence left behind. What they found inside the collapsed cliffs changed the direction of the entire investigation. At first glance, the exposed rock face looked like any other coastal bluff. Layers of sand, gravel, and sediment stacked over thousands of years by wind, waves, and time. But just meters above the fresh break line, something didn't belong. A thin, dark band cut cleanly across the cliff. It wasn't supposed to be there. The layer that raised alarms. This layer stood out immediately. It was darker than surrounding material, almost black in certain lighting. Its texture was fine and compact, not loose or sandy like typical coastal deposit. When researchers ran their fingers across it, the sediment felt dense, almost waxy. More troubling was its position. Based on geological models, material like this should only form in deep marine environments, far below the reach of coastal cliffs. Yet here it was, exposed to open air after the collapse. Samples were taken carefully, photographed, logged with GPS coordinates, sealed and rushed to laboratories across the state. Even before testing began, one feature stood out. The sediment shimmered. Under sunlight, it reflected faint metallic flecks, a subtle sheen that shouldn't exist in normal shoreline rock. That alone was enough to elevate the site from erosion study to full geological investigation. Looking beneath the surface, to understand how widespread the anomaly might be, teams deployed ground-penetrating radar across the surrounding area. Normally, radar scans reveal clean boundaries where loose material ends and solid bedrock begin. That is not what appeared on the screens. Instead, large sections beneath the cliff returned weak or distorted signals. Radar energy scattered unpredictably or disappeared entirely. These shadow zones stretched tens of meters wide and were centered deep below the surface. At first, engineers assumed equipment failure. They recalibrated. They reran the scans. They swapped instruments. The results didn't change. Whatever lay beneath the ground was not behaving like solid rock. If those shadowed regions represented weakened or altered material, then the cliff hadn't collapsed simply because of wave action. It had lost its support from underneath, slowly, invisibly, over time. The lab results no one expected. When the samples arrived under scanning electron microscopes, the results were immediate and unsettling. Elemental mapping revealed unusually high concentrations of manganese and iron, far higher than what is normally found in coastal environments. Even trace ratios didn't match known shoreline sediment profiles. Further testing confirmed it. manganese oxides, iron-rich compounds. Mineral structures typically associated with deep-sea nodules, formations that grow on the ocean floor thousands of meters below the surface over millions of years. These materials do not form in coastal cliffs. They do not migrate upward naturally, and they do not appear overnight. So how did they get there? A theory takes shape. One explanation began to dominate discussions: upward fluid migration. Under certain conditions, pressurized fluids trapped deep within Earth's crust can travel upward through fractures and faults. As they move, they carry dissolved minerals with them. Over time, those minerals precipitate, forming dense layers in places they don't belong. If this process had been active beneath California's coast, it could explain everything: the slow seismic signals, the weakened subsurface, the strange mineral deposits, and most importantly, the sudden loss of structural integrity. In this scenario, the cliff didn't fail because waves eroded it from the outside. It failed because the ground beneath it had already been altered, softened, fractured, chemically chained. The collapse was just the final symptom. A larger pattern emerges. As scientists compared notes, similar findings began surfacing elsewhere. Not just one cliff, not just one location. Dark sediment layers appeared in multiple collapse zones along the coast. Radar shadow regions overlapped with areas of increased subsidence. Seismic anomalies aligned with known deep fault systems previously considered inactive. Individually, each clue might be dismissed. Together, they painted a troubling picture. A system-wide process was at work beneath the coastline, and it wasn't finished. Why this changes everything. If deep subsurface fluids were actively weakening coastal foundations, then traditional erosion models were incomplete. Protective measures like seawalls and barriers only address surface forces. They do nothing for instability rising from below. This realization forced scientists to reconsider decades of assumption. Coastal safety had always been framed as a battle against waves and storm. But what if the real threat was underground? What if entire stretches of land were resting on compromised foundations, waiting for the next trigger? The silence between events. Perhaps the most disturbing aspect was what wasn't happening. No major earthquakes, no dramatic warning signs, just slow, continuous change. This kind of process doesn't announce itself with a single catastrophic moment. It progresses quietly, weakening structures until failure becomes inevitable. By the time cliffs collapse or roads give way, the damage has already been done. And that meant something else. Other sections of the coast could already be compromised without anyone knowing. A question with no easy answer. As researchers compiled their findings, one question loomed larger than the rest. If these materials came from deep below the ocean floor, what activated the process? Rising sea pressure, tectonic stress redistribution, climate-driven changes in groundwater systems, or a combination no model has fully accounted for yet. The answers mattered because understanding the cause meant predicting what comes next. And right now, the coastline wasn't just eroding, it was being rewritten. By the time scientists stepped back from the data, one conclusion had become impossible to ignore. The collapse was not an isolated event. It was a warning. Why traditional models failed. For decades, coastal risk models focused on visible forces: waves, storm surge, rising sea levels. Engineers designed protections based on what they could see attacking the shoreline. But the evidence now suggested something far more dangerous. The ground itself was changing. Subsurface weakening doesn't follow the same rules as erosion. It doesn't require storms or earthquakes. It happens silently over years, sometimes decades, beneath layers of earth that appear perfectly stable from above. This is why the collapse came without warning. No dramatic cracks, no widening fissures, no visible signs of imminent failure. The cliff gave way because its internal structure had already failed. How much time is there? That question became the center of every briefing. How much warning can these processes provide? The honest answer unsettled even seasoned experts. Possibly none. Slow slip events and fluid migration do not produce sharp signals. They unfold gradually, blurring into background seismic noise. By the time surface deformation becomes measurable, collapse may already be inevitable. In several analyzed cases, radar data suggested subsurface weakening had begun years before failure. The land didn't fall suddenly. It surrendered. What this means for coastal cities. If cliffs and bluffs can lose their foundations without surface indicators, then the implications extend far beyond uninhabited shoreline. Highways, residential neighborhoods, critical infrastructure, ports and power corridors. Much of California's coastline is built on similar geological framework: sedimentary layers over fractured bedrock, fault systems interlaced with fluid pathways, pressure zones influenced by both tectonics and hydrology. If even a fraction of these areas are undergoing the same unseen transformation, the risk profile changes completely. Coastal collapse is no longer a question of if storms will hit. It becomes a question of where the ground will fail next. Monitoring the invisible. In response, agencies have begun rethinking how coastlines are monitored. Traditional surveys are no longer enough. New strategies focus on detecting what cannot be seen. Microseismic arrays tuned to slow slip signatures. Continuous radar scanning of subsurface reflectivity. Chemical analysis of groundwater near fault zones. Satellite measurements tracking millimeter-scale ground movement. But even with advanced technology, coverage remains limited. Monitoring every mile of coastline at depth is neither simple nor cheap, which means uncertainty remains. Why this is a global problem. While the investigation began in California, researchers quickly realized this phenomenon isn't unique. Similar geological conditions exist worldwide. Japan, Italy, Chile, Indonesia, the Pacific Northwest. Anywhere tectonic systems meet coastlines, the same processes may be unfolding quietly beneath the surface. The difference is awareness. Most collapses are still being labeled as erosion or weather-related failures, but without subsurface analysis, many warning signs go unnoticed. The science is catching up, but slowly. The psychological risk. There is another factor scientists rarely discuss publicly. Human perception. People trust what looks solid. Cliffs don't feel dangerous until they move. Ground feels safe until it breaks. Coasts appear permanent because they change slowly. That false sense of stability is one of the greatest risks. When warning signs are invisible, preparedness drops. Evacuation planning becomes harder. Public urgency fades. And by the time reality asserts itself, there is no room left to react. The next failure won't look the same. Perhaps the most unsettling conclusion was this. The next collapse may not resemble the last one. It might not involve a cliff. It might not be dramatic. It might not even occur near the ocean. Subsurface weakening can destabilize slopes inland, undermine foundations, and amplify damage during moderate seismic events that would otherwise cause little harm. What failed here was not just rock. It was an assumption. What scientists are watching now. Right now, teams are watching specific signals closely. Unexplained low-frequency tremors, persistent radar shadow zones, chemical anomalies in groundwater, clusters of microfracturing beneath populated coastlines. None of these guarantee collapse, but together they suggest something is still moving, still adjusting, still unfinished. Final reality. Earth doesn't need to erupt or quake violently to reshape the land. Sometimes it only needs time, slow pressure, silent movement, unseen change. By the time the coastline gives way, the process has already run its course. The collapse we witnessed wasn't the beginning. It was the evidence, and somewhere beneath the ground, the same forces are still at work, waiting,